Okay, this is the second video for extension to mathematical induction. The second type that we're going to look at are inequalities. Just going to look at some past HSC examples. This first question is HSC 2004, question 7a. So let a be a positive number. Show that a plus 1 on a is greater than or equal to 2. It's very straightforward. You can start with a minus 1 squared is greater than or equal to 0, as a is greater than 0, and equality if and only if a equals 1. All right, because we know that a is a positive number. So therefore a squared minus 2a plus 1 is greater than or equal to 0. Therefore, a squared plus 1 is greater than or equal to 2a. And now dividing through by a, and we know that, remember that a is positive, we get that a squared on a plus 1 on a is greater than or equal to 2a on a. So therefore, a plus 1 on a is greater than or equal to 2 as required. Part 2 of the question is the induction bit. For part 2, let n be a positive integer and a1, a2 all the way up to an be n positive real numbers. Prove by induction that a1 plus a2 all the way up to a sub n times 1 over a sub 1 plus 1 over a sub 2 plus all the way up to 1 over a sub n is greater than or equal to n squared. So step 1, prove true for n equals 1. Okay. Left hand side will be a1 times 1 over a1, which is 1, which is of course greater than or equal to 1 squared. So therefore true for n equals 1. So 1 squared is 1. Assume true for n equals k. That is, we're assuming that a1 plus a sub 2 plus all the way up to a sub k times 1 over a sub 1 plus 1 over a sub 2 plus all up to 1 over a sub k is greater than or equal to k squared. And step 3, prove true for n equals k plus 1. That is, we want to prove that a sub 1 plus a sub 2 plus a sub k plus a sub k plus 1 times 1 over a sub 1 plus 1 over a sub 2 plus all the way up to 1 over a sub k and 1 over a sub k plus 1 is greater than or equal to k plus 1 squared. Okay, starting with our left hand side, we can see here in our first bracket that we really have the sum of all terms from n is 1 through to n is k plus 1 of a sub n times the sum of all terms here from, again, n is 1 to n is k plus 1 for 1 over a n. Now, so that we can use the assumption, we're going to break this up from 1 to k and then add on the k plus 1th term. So in our first bracket, this is really the sum from n is 1 to k of an plus, we have this term here, this a k plus 1th term, times the sum from n is 1 to k of this 1 over a to the n plus, so we've got all of this is represented by that, plus 1 over a to the k sub k plus 1. Okay? Now we're going to use, we'll multiply out here first, we'll expand. So therefore, just using the for method, this is the sum from n is 1 to k of a to the n times the sum from n is 1 to k of 1 over a to the n plus, so that's the first thing, plus the outer terms, 1 over a k plus 1 times the sum from n is 1 to k of a to the n plus the two inner terms, a sub k plus 1 times the sum of from n is 1 to k of 1 over a sub n sorry about that, plus these last two terms multiplied by each other, a sub k plus 1 times 1 over a sub k plus 1 will be just a sub k plus 1 over a sub k plus 1. Our assumption is that from a sub 1 up to a sub k times 1 over a sub 1 all the way up to 1 over a sub k, that those two multiplied by each other, those two expressions multiplied by each other, or summations, is greater than or equal to k squared, and that's what we've got here. The sum from n is 1 to k of a sub n times the sum from n is 1 to k of 1 over a sub n. So therefore that is greater than or equal to k squared plus, and writing the rest of this out, 1 over a sub k plus 1 times sum from n is 1 to k a n plus a sub k plus 1 sum from n is 1 to k 1 over a sub n plus 1 a sub k plus 1 over a sub k plus 1 is 1. Now this is equivalent to k squared plus, now if this gets multiplied by each of these summations, then it'll just be the sum from n is 1 to k of a sub n over, actually I probably, oh, that was meant to be a k, sorry, I need to go back here and make these k's. Okay, so that's a sub k, sorry about that, that's a sub k, a sub k, a sub k, a sub k. Actually, no, the n's, sorry, just fix them up, sorry about that. Oh, now I've got to fix them up. So there, n's, just make them n's. So a sub n over a sub k plus 1 plus sum from n is 1 to k of a sub k plus 1 over a sub n plus 1. This is the, so noticing we're summing from n is 1 to k for these two things, so we'll combine them together. So sum from n is 1 to k of a sub n over a sub k plus 1 plus a sub k plus 1 over a sub n, sum of all that, actually I'll go like this, plus 1, which equals k squared plus, remember we're trying to just get that it's greater than or equal to k plus 1 squared. So we're going to need, so we'll just keep working here. Now here, notice that this is just the reciprocal of that, so it's sum from n is 1 to k over a sub n, a sub k plus 1 plus 1 over a sub n over a sub k plus 1 plus 1. Now let's go back to part 1. Part 1, we know that a plus 1 on a is greater than or equal to 2. Now this is of that format, a plus 1 on a is greater than or equal to 2. So therefore, this is greater than or equal to k squared plus sum from n is 1 to k of 2 plus 1. So replacing this with greater than or equal to 2. To k squared plus 2 times k, because it finishes with k, plus 1, which equals k plus 1 squared. And therefore we have our desired result. And so therefore, we're trying to prove, therefore all of that left-hand side, therefore a1 plus a2 plus ak plus 1 times 1 over a1 plus 1 over a2 plus all the way up to 1 over ak and 1 over ak plus 1 is greater than or equal to k plus 1 squared by mathematical induction. Therefore proven true by mathematical induction for n greater than or equal to 1. So proven true. Now just clarifying this 2k here, 2 is occurring k times, which is why it is 2k, 2 times k, because it's k lots of 2 if this 2 occurs k times. So it's 2 plus 2 plus 2 plus 2 all the way up to k times, so therefore we get 2 times k. So that's how we go from this step here to that 2k there. Okay, this is 1985 HSC, question 8, part 2. This particular question is referred to in the Board of Studies as an example that should be looked at. So show that for k greater than or equal to 0, that 2k plus 3 is greater than 2 times the square root of k plus 1 times the square root of k plus 2. Okay, so we know that 2k plus 3 is equal to the square root of 2k plus 3 squared, which is the square root of 4k squared plus 2 times 2k times 3, which is plus 12k plus 9. And the right hand side, which is 2 times the square root of k plus 1, k plus 2, is equal to, we know that 2 is the square root of 4, so it's equal to 4 times the square root of k plus 1 times k plus 2, which is the square root of 4k squared plus 3k plus 3, which is equal to the square root of 4k squared plus 12k plus 12. Okay, a little mistake here, that's a 2, k squared plus 3k plus 2, and this here is an 8, which is why it wasn't working. So therefore we can say that 2k, so that is greater than, so we can say that this is obviously less than square root of 4k squared plus 12k plus 9. So since the square root of 4k squared plus 12k plus 9 is greater than the square root of 4k squared plus 12k plus 8, therefore 2k plus 3 is greater than 2 times the square root of k plus 1 times the square root of k plus 2. So that's part question A. So this is question 8A part 1. Now for question, just 8A. Now for question part B of this question. Next question is to prove that for n greater than or equal to 1, that 1 plus 1 over root 2 plus 1 over root 3 plus all the way up to 1 over root n is greater than 2 times the square root of n plus 1 in brackets minus 1 close brackets. Okay, so prove that for n greater than 1 that this holds, of course, by mathematical induction. So for n equals 1, our left hand side equals 1 over the square root of 1, which is 1, and our right hand side is equal to 2 times the square root of 1 plus 1 minus 1, which is 2 root 2 minus 1, times, wait, I've got brackets here, times root 2 minus 1, which is approximately equal to 0.828. So therefore, obviously the left-hand side is greater than the right-hand side, so 1 is greater than 0.828, so therefore true for n equals 1. Step 2, we're going to assume true for n equals k. So 1 plus 1 over root 2 plus 1 over root 3 plus 1 over the square root of k is greater than 2 times the square root of k plus 1 minus 1. Step 3, prove true for n equals k plus 1. So that is, we need to prove that 1 plus 1 over root 2 plus 1 over root 3 plus all the way up to 1 over root k plus 1 over root k plus 1 is greater than 2 times the square root of k plus 1, which is 2 times the square root of k plus 2 minus 1. We know that 1 plus 1 on root 2 all the way up to 1 plus 1 on root k is greater than 2 brackets square root of k plus 1 minus 1. So therefore this is greater than 2 brackets square root of k plus 1 minus 1, then we've got this term plus 1 over the square root of k plus 1. Now, making a common denominator, this is equal to 2 times the square root of k plus 1, bracket, square root of k plus 1 minus 1, plus 1, all over the square root of k plus 1, which is 2 times k plus 1 minus 2 times the square root of k plus 1 plus 1 over the square root of k plus 1. So continuing from there, that is equal to 2k plus 2 plus 1, which is 2k plus 3, minus 2 times the square root of k plus 1 over the square root of k plus 1. Now we know from part 1 that 2k plus 3, we've proven that it's greater than 2 bracket k plus 1 times k plus 2. So therefore this is greater than 2 times the square root of k plus 1 times the square root of k plus 2 minus 2 times the square root of k plus 1 all over the square root of k plus 1. Now we can now divide by square root of k plus 1, so this is 2 times the square root of k plus 1 times the square root of k plus 2 over the square root of k plus 1 minus 2 times the square root of k plus 1 over the square root of k plus 1, which equals 2 times the square root of k plus 2 minus 2, which is equal to 2 times the square root of k plus 2 minus 1 in brackets. So therefore it's proven true by mathematical induction. So proven true by mathematical induction for n greater than or equal to 1. Question part C is the statement that for all positive integers n, that the sum from k to 1 through to capital N of 1 over the square root of k less than 10 to the power of 10 true. Give reasons for your answer. The sum from k equals 1 to n of 1 over the square root of k is 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus all the way up to 1 over the square root of k. Now we know from part 1 we did the same induction question and we proved that we had to prove that 1 plus all of this up to square root of n is greater than 2 times the square root of n plus 1 minus 1, and we did prove that by mathematical induction. So that therefore is greater than 2 times the square root of k plus 2 minus 1. This is from part B above that we just did. B1, I just wrote that down wrong. Okay, 2 times the square root of k plus 1 minus 1. So we can find n so that 2 times the square root of n plus 1 minus 1 is greater than or equal to 10 to the power of 10, because we're trying to see whether if it is less than 10 to the power of 10. So to see whether it's less than 10 to the power of 10, if we can find n such that it's greater than 10 or equal to 10 to the power of 10, that is the opposite situation of that. So therefore, if we divide, so if we start with that, so we've got 2 times the square root of n plus 1 minus 1 is greater than or equal to 10 to the power of 10. If I divide by 2 or multiply both sides by a half, I get square root of n plus 1 minus 1 is greater than or equal to 1/2 times 10 to the power of 10. In other words, square root of n plus 1 minus 1. Now this is greater than or equal to 1/2 times 10 to the power of 9. So square root of n plus 1 is greater than or equal to 1/2 of 10 is 5 times 10 to the power of 9, and plus 1, bringing this one to the other side. So if we square both sides, so squaring both sides, we get that n plus 1 is greater than or equal to 5 times 10 to the power of 9 plus 1 squared. Plus n is greater than or equal to 5 times 10 to the power of 9 plus 1 squared minus 1. For n greater than or equal to 5 times 10 to the power of 9 plus 1 squared minus 1. So if we take n greater than or equal to that, then this sum from k to 1 to n of 1 over the square root of k will be greater than or equal to 10 to the power of 10. And so therefore that statement up there is not true. So therefore the statement that sum from k to 1 to n of 1 over the square root of k is less than 10 to the power of 10 is not true. Okay. The example from the 1999 HSC question 6a, let x be a fixed non-zero number satisfying x greater than 1. Use the method of mathematical induction to prove that 1 plus x to the power of n is greater than 1 plus n times x for n equals 2, 3, etc. Okay, step 1, prove true for n equals 2. Now our left-hand side, we've got 1 plus x squared is equal to 1 plus 2x plus x squared, and that is greater than, which is greater than 1 plus 2x, since x cannot equal 0. Therefore, it's true for n, in other words, greater than 1 plus 2x, in other words, which happens to be the right-hand side for n equals 2. Therefore, true for n equals 2. Assume true for n equals k. We're assuming that 1 plus x to the power of k is greater than 1 plus kx. And step 3 is to prove that it's true for n equals k plus 1. That is, we are trying to prove that 1 plus x to the power of k plus 1 is greater than 1 plus k plus 1 times x. Okay, starting with our left-hand side. 1 plus x to the power of k plus 1 is equal to 1 plus x to the k times 1 plus x to the power of 1, which is greater than, now 1 plus x to the k is greater than 1 plus kx, so that's greater than 1 plus kx times 1 plus x. This is using the assumption, and that is equal to 1 plus x plus kx squared, which equals 1 plus x times 1 plus k plus kx squared. Now that, we're trying to prove that, that this is greater than that, and it is, which is greater than 1 plus, I'm just going to write this as k plus 1 times x, because that is greater than 1 plus k plus 1 times x, because these two are that, plus we've got the k squared here. The reason is since k times x squared is greater than 0, because we know that k is greater than 2. Okay, therefore this is proven true by mathematical induction. Now for the second part of the question, we have to deduce that 1 minus 1 over 2n all to the power of n is greater than a half for n equals 2, 3, and so on. Our result from part 1 that we've just proven true that 1 plus x to the power of n is greater than 1 plus n times x. So if we let x equal negative 1 over 2n and substitute it in here, we need to come up with an expression for nx as well. So therefore nx will equal negative 1/2 as well. So therefore we have, probably may not use that yet. So therefore replacing the x with x equals negative 1 over 2n, we will get that 1 minus 1 over 2n all to the power of n will be greater than 1. Now we know that nx is minus a half. 1 minus a half. Okay? In other words, 1 minus 1 over 2n to the power of n is greater than a half. And so therefore we've deduced that result that 1 minus 1 over 2n to the power of n is greater than a half. Okay? All for induction with inequalities.